SwayamPrabha. Digital India. Educated India.
So, welcome to today class of nonlinear vibration. So, in this module we are discussing regarding the numerical tools used in this nonlinear vibration course. So, today class we are going to study regarding the time response, FFT, Poincare section and Lyapunov exponents, which are very much useful or required in this course. So, already you are acquainted with the time response. So, generally in time response we used, so given a differential equation we solve that equations and plot the time response of the system. For example, so you have studied regarding this equation for a spring mass system. So, mx double dot plus kx plus cx dot equal to f sin omega t. So, you have studied both free and force vibration response. So, in case of free vibration, so this part equal to 0 and you have plotted for 3 different type of damping, that is under damped and then critically damped and over damped case, and you have plotted the response. So, time response you are, so for example, this x versus t you have plotted and you have seen. So, in case of the under damped system, so it will damp out and this will be 0. So, this line, so you can take that this line is the 0 line. So, this is 0. So, you can plot this x versus t. So, from a given initial point, so you can plot the time response taking. So, when you are using this archetype, this Runge-Kutta methods, you can use 4th and 5th order Runge-Kutta or ODE 4-5 in MATLAB. So, you have used this ODE 4-5 in the MATLAB to plot this thing. So, differential equation solutions. So, in case of the forced vibration also, so if you have a force, for example, this let this omega equal to 2 and this k by E, so this is mx double dot you can take. So, omega n, so which is root over k by m, so let it is equal to 1. So, in that case, so the system will have two frequency oscillation. So, one is the 1, that frequency omega n equal to 1. So, you can find omega d. So, omega d equal to omega n into root over 1 minus zeta square. So, this is the damped natural frequency. So, system has the damped natural frequency. So, one frequency will be damped natural frequency and other one will be external frequency. So, it will have a transient part with omega d, and then so it will have a particular integral or the steady state response with a frequency of 2 radian per second. So, you will have a periodic response with 2 radian per second, that will be the steady state response, but the general solution will contain two frequency. So, one is omega d and other one is omega. Similarly, you may study the maps also. So, here you can see the logistic map, cubic logistic map, then taint map. So, there are several maps are also there where you can plot or where you can plot the x n plus 1 or where you can write this x n plus 1 equal to f x equal to k x n into 1 minus x n. So, this is the logistic map. So, cubic order logistic map, you can write this x n plus 1 equal to k x n minus x n cube. So, starting with x 0. So, here your n will start from 0. So, n equal to 0, 1, 2 like that. So, iterations or different iterations you can have. So, here we have plotted this logistic map. So, taking this k equal to 0.25. So, starting with x 0. So, we have taken 500 iteration. So, n we have taken equal to 0 to 500 we have taken. So, you can see, so in that logistic map by taking k equal to 0.25. So, this equation will reduce to 0.25 into xn into 1 minus xn. So, for example, so our x1 will be, in case of logistic map, x1 will be equal to k we have taken 0.25. So, 0.25 into x 0 minus x 0 square. Similarly, x 2 will be equal to 0.25 into, so this is x 1. So, the previous point we are taking, that is x 1 minus x 1 square. Similarly, x 3 will be equal to 0.25 into x 2 minus x 2 square. So, this way you can expand this thing, and if you plot this 1, 2, 3. So, that is starting with x 0. So, if you are plotting this side, this is 0, 0, 1, 2, 3, 4 like that, and in y axis if you are plotting this x n plus 1. So, the curve what you are getting, so that is the logistic map. So, you just see for k equal to 0.25. So, we got this value, and k. So, we are taking this initial x 0 equal to, so here x 0 we are taking equal to 0.1. So, starting the x 0 equal to 0.1. So, it depends on the initial conditions what you are taking. So, starting x 0 equal to 0.1. So, if you plot for a different value of k, so you can see the response to be chaotic for k equal to 4. So, it is single periodic. So, this is periodic response you are getting here, and then so period doubling occurs. So, you have period doubling root to chaos. So, this is for k equal to 3. So, k equal to 3. So, 2 lines you are able to see. So, here you have 4 lines, here you have a single periodic, then 2 period, then 4 period, and finally, you have a chaotic response. Similarly, for cubic logistic map. So, you can see for cubic logistic map. So, x n plus 1 equal to k x n minus x n cube. So, similarly, here also you can start with k for different value of k and starting with an x 0 value. So, you can also get the chaotic response. So, if you plot this x n plus 1 versus x n, so this is the curve. So, this is x n plus 1 versus x n. So, this is the chaotic for k equal to 3. So, this is plotted. So, to find the fixed point response, so you can draw a line. So, you can see in this case, if you draw a line at an angle of 45 degree. So, you can see, so it is cutting. So, these are the fixed point. So, 3 fixed point you are getting. So, 3 period 3 you are getting. So, already you know a theorem is there. So, occurrence of period 3 response shows the existence of a chaotic response. So, you can see, so this is a chaotic response seen in this case of cubic logistic map with k equal to 3. So, here we have started x 0 equal to 0.1. So, we have started x 0 equal to 0.1, and so this is the curve. So, in this case if you are plotting, so this is starting with 0.1. So, if you join, so if you draw a 45 line, so you can see, so you have only a single periodic response. So, one periodic, now you have seen this chaotic response. So, in the previous case you have seen this period doubling root to chaos. So, this way you can plot the curves. So, in logistic map by bifurcation curve diagram you can also plot. So, initially single periodic, then 2 periodic, then 4 periodic, then you can see from each point. So, another 2 are there. So, this is 8 periodic, then 16 periodic. So, that way it will go, and in between. So, these are the chaotic response, and in some places you can see there are some windows. So, for example, here you have a window of 3 periodic. So, at 3 positions you have these 3 points are there, otherwise it is blank. So, sometimes there is compression in the trajectory, and sometimes there is enlargement of the trajectory in case of the chaotic response. So, this part you can see these are the chaotic response. So, here you have single period, then 2 period, then this 2 period bifurcate to have 4 period, then 8 period, 16 period, and so then finally you have chaotic response, and in this chaotic regime. So, you have seen some windows of periodic response. So, by varying the system parameter, so you can see, so you can operate the system at different type of response, single periodic, 2 periodic, then 4 periodic, or chaotic response regime you can operate. So, previously also you have seen this doping equation, and you have plotted this displacement versus time, then this phase portrait also plotted. So, you have seen this, particularly this equation, this is the doping equation, x double dot plus delta x dot plus alpha x plus beta q equal to r cos omega t. So, if you are taking, so here alpha is taken to be 1, beta equal to 5, delta equal to 0.02, r equal to 8, and omega equal to 0.5. So, these are the curves one can obtain. So, here clearly you can see the response to be chaotic response. So, you have already seen this fixed point response also for some value of this thing. So, you can have fixed point response, for some value you can have periodic, some value you can have quasi periodic and chaotic response. So, you can write a small code for finding this phase portrait and this time response. So, here the code is written, and here a MATLAB code is written. So, here the t span equal to 0 to 100, x 0 equal to 1 to 0. So, t x equal to OD45 SOL. So, this is the function file where you are writing the doping equation. So, using this first order equation, then t span x 0 is the initial conditions you are giving. So, you can have this displacement can be stored in this x, and this column 1, and this velocity is stored in this column 2 of the x. So, you can plot this, plot t command displacement. So, this way, or for phase portrait you can plot this velocity and displacement, you can change. So, it is, so displacement, so here it is written slightly wrongly. So, this is y level is velocity and x level is displacement. So, you can plot this way. So, this is the function solve where we have written. So, you just see, so this is the equation. So, it is written in first order form. So, for example, for a simple equation, let me write in first order form, then x double dot, for example, x double dot equal to, you can write for the equation x double dot plus kx or mx double dot plus kx plus cx dot equal to f. So, you can write x double dot equal to f minus, so this is equal to minus k f by m minus k by m x. So, this is plus, and then minus c by m x dot. So, you can write this as f by m. So, this k by m is nothing but this omega n square x minus 2 zeta omega n x dot also. So, by taking this x equal to, for example, let me take x equal to y1 and x dot equal to y2. So, and writing this dy1 equal to, so dy1 will be equal to x dot and dy2 will be equal to y dot. So, our equations will reduce to this form, or here it is written x d 1 2 3 4. So, this is another equation is written. So, So, in this equation this is xd1 equal to minus x2 plus x3. Okay, so this is for another attractor, Lorentz attractor, this is written. You can write your own code for different value of this dumping oscillator. So, here it is for periodic. So, that thing you can see here we have written this one, different cases we have taken, and for different cases different values we have taken and they have been plotted. Okay, so, you have seen periodic, then other type of periodic, then chaotic responses are there. Similarly, for van der Pol equation also you can write your own code and you can use this ODE45 to plot this phase portrait and time response. So, in this case you know it will lead to a limit cycle. So, this is the limit cycle. So, this is the starting point or this is the starting point. So, starting from here. So, you can see this is a limit cycle you are getting. Similarly, starting from here. So, you can see a limit cycle you are getting in case of the van der Pol oscillator. So, this is the time response, then you can plot. So, in this nonlinear analysis you can plot the frequency response plot also. So, sometimes you will get the closed form solution, for example, in case of the single degree of freedom system with force vibration. So, you got, so this is the magnification factor versus omega by omega n, or the displacement versus omega by omega n is known as the frequency response plot. So, here you can know that at omega equal to omega n, so with a system without damping, so it will go to infinite, and due to the presence of damping, so it will limited and you will get different value or different maximum value of the response. So, this thing already you know. So, the maximum or at omega by omega n, this is equal to 1 by 2 zeta. So, this is the phase portrait, this is the phase diagram also. So, this is the frequency response and this is the phase response of the system. So, that is for a single degree of freedom system, and for a 2 degrees of freedom system you can see. So, we have 2 peaks and at omega by omega n. So, if it is a tuned vibration observer, then at omega by omega n this x1 equal to 0. Similarly, for, so this is for linear system. So, when you are taking nonlinear system, for example, in case of the doping equation, so these are for different. So, this is for doping equation with cubic nonlinearity, and that equation can be written in this form: x double dot plus omega n square x plus 2 zeta omega n x dot. So, this is equal to f sin omega t, or k sin omega t, it is written k sin omega t. So, this form you can write. So, here this k and zeta, so they are of order of epsilon, and so we have weak nonlinearity in this case. Okay, so this alpha epsilon, so you can add this alpha xq also. So, this is the nonlinear term. So, these three are the linear term, then the nonlinear term, and right side you have a forcing term. So, in that case you can have this hardening effect or softening effect. This is the softening effect and this is the hardening effect. So, depending on the value of alpha you can get. So, similarly for other systems also, so you can have this so trivial state in stability region, supercritical pitch for bifurcation. This is the subcritical pitch for bifurcation, this is the supercritical bifurcation, and here also you can have a, so here only the response is only non-trivial state, and here you can have a saddle node bifurcation points. So, these responses, these frequency responses are for nonlinear systems. So, in nonlinear systems, so either it can bend to right or left, or so it will not be, so at omega equal to omega n, so it is not equal to infinite. So, here the nonlinearity limits the vibration of the system. So, then, so already you have familiar with this figure. So, here you have seen, so for systems with internal resonance conditions you have seen. So, we have multiple responses are there in frequency response, unlike in case of the single degree of freedom systems, where we have only one response for a particular value of omega n. Here for a particular value of omega n, we can have multi branches solutions or multiple solutions. So, out of which some of them may be stable and some of them may be unstable, and here we have multiple bifurcation points are also there. Sometimes we can have the supercritical pitch for bifurcation, subcritical pitch for bifurcation, then the saddle node bifurcation, hop bifurcation. So, all these type of bifurcations we can observe. So, in case of the trivial and non-trivial state of the system. So, to plot this bifurcation diagram or to plot this frequency response, so you must have to solve these equations using. So, you have a set of equations, for example, so in this case, so we have 4 equations are there. So, we have the equation, this reduced equation with A1 dot, gamma 1 dot, A2 dot and gamma 2 dot. So, 4 equations we had. So, these 4 equations, so this is a function of A1, A2, gamma 1, gamma 2 and also sigma detuning parameter. So, all of them are function of similarly are F1. So, this is G1. So, this is I can write this is F2 and this is G2. So, all of them are function of A1, A2, gamma 1, gamma 2 and sigmas and also different system parameter. So, they are function of different system parameters also. So, by varying the system parameters, so you have to get different response, but how to do this thing? So, you have to solve these. So, for steady state, so these 4 terms will be equal to 0. So, this will reduce to that of a transcendental equation, and you have to solve this transcendental equation, algebraic and transcendental equation, by using this Newton's method. So, you can use this Newton's method. So, already we have seen this Newton's method. So, by using Newton's method, so you have to solve it. So, due to the presence of multiple branch, so depending on the initial conditions in the Newton's method, so it will go to a particular branch. So, you have to take several initial conditions to get this complete response. So, there are several continuation techniques are also there. For example, you have started with some bifurcation points. So, then how you have to continue. So, for that purpose there are several continuation techniques are there. So, for fixed point responses you can have the sequential continuation technique or Kubitschek-Marek. So, this is developed by Kubitschek-Marek in 1983. Then this Davydenko Newton-Raphson continuation, arc length continuation techniques are there. Then you can have the pseudo arc length continuation technique. Then for periodic response you can use the shooting method, arc length continuation method, pseudo arc length continuation method. So, for more details, so you can see the book by Nafe and Balchandran on applied nonlinear dynamics. So, you can study the detail regarding these continuation techniques from that paper or that book, but to easily find all these responses, initially take some arbitrary initial conditions, find some responses, find the steady state response and take those steady state response as the initial condition and run this Newton method to find all the branches of the solution. So, this way it has actually been plotted, but one can use these continuation techniques to find the responses also. Now, let us come to, so now you know regarding these time response and frequency response. So, these two are very important in studying the nonlinear dynamics course. So, after getting the time response, so this time response we may get theoretically or from our simulation, or you may have some experimental data where you have the time this displacement versus time plot, or velocity versus time plot, or acceleration versus time plots also, or the time response of the systems are known to you. So, how to analyze those time response? So, already you know, so you have different type of time response. So, it may be fixed point. So, in case of fixed point, so it will have a fixed value. So, this is the fixed point response. So, time t. So, for example, let me plot A versus t. So, A is the response amplitude and t is the time. So, in case of a fixed point response, you have a fixed value. Sometimes what will happen, so you may have a, so you can have other different, for example, so you may have a periodic response also. So, you may have a periodic response. Sometimes you may have quasi periodic response also. So, where you can have two frequency and those frequencies are commensurable. For example, you can have this y equal to 5 sin 2t plus 5 sin 2 root 2t. So, here omega 1 equal to 2 and omega 2 equal to 2 root 2, and here this omega 2 by omega 1 equal to root 2. So, this is an irrational number. So, in that case the response will be quasi periodic. So, sometimes you have these multiple harmonics also. So, in the time response multiple harmonic terms may be present. So, to get how many frequencies are there in that corresponding response, so you can plot these fast Fourier transform FFT. So, we should know how to plot this FFT. So, a brief regarding this FFT I am going to tell you now, and then so there are other methods also to characterize the response. So, we will see how we can use this Poincare section to characterize this fixed point, periodic, quasi periodic response, and also we will see later that the Lyapunov exponent method also may be used to study different type of response. So, let us see. So, FFT is a computationally efficient way to compute the discrete Fourier transform. So, before learning about FFT algorithm, we need to take a look at the DFT. So, DFT is a mathematical transformation that can be written in terms of a matrix multiplication, but DFT require a large number of matrix multiplication which computationally is expensive. So, DFT is a n square order calculation where n is the number of data points at which the function value are given. To compute DFT more efficiently, Cooley and Tukey came up with this FFT algorithm in 1965. So, before that Gauss invented the theory, so but it was not published. So, already you know regarding the, so for example, let you have a function f with time. So, if you plot this thing, so for a continuous function, so you know, so you have a continuous curve is there, but sometimes when we are doing experiments, so instead of this continuous time data, so we sample the time data at discrete interval of time. So, in that case instead of getting a continuous curve, so we are having the discrete points. So, for example, so these are the discrete points at which, so we have evaluated the functional value of the system. So, for example, at x0, so this is the value, x1 this is the value, x2 this is the value. So, this x0, x1, x2 may be similar to this time t, or it may be the number of iteration at which you are finding the response, or you are noting down the response, or you are sampling the response. So, let us assume that there are n number of data points. We have started with 0. So, the final data point, as we are taking n data point, the final data point will be n minus 1. So, we have x0 to xn minus 1. So, we have taken this n number of points. So, this function f we can write in this way. So, the function f can be written as f j e to the power minus I 2 pi jk by n. So, already you know the Fourier transform. So, this f cap can be written by using this function f this way. So, f k can be written as j equal to 0 to n minus 1 f j e to the power minus I 2 pi j k by n. Similarly, f k can be written. So, this is f j what is written. So, that inverse transform also you can do. So, you can write this f k equal to 1 by n, j equal to j to n minus j equal to 0 to n minus 1 f j cap e to the power 2 I 2 I pi j k by n. So, if we are taking, let us take this omega n equal to e to the power minus 2 I pi by n. So, where I equal to root over minus 1, then this transform f k cap and f j we can write. For example, now you just take, let k equal to 0. So, f 0. So, let us find f 0 cap. So, f 0 cap will be equal to, so now j is starting from 0. So, this is f 0. So, it can be written as f 0. So, e to the power. So, now this is, so we are taking n. So, now you just take this k is taken to be 0. So, as k is taken to be 0. So, e to the power 0 equal to 1. So, this becomes f 0. So, then plus next term let us find. So, next term will be, so j equal to 1. So, this will becomes f 1. So, f 1 into e to the power. So, this is e to the power minus 2 I pi. So, k already we have taken. So, this is 0. So, this is into 0. So, this becomes 0. So, it becomes e to the power 0. So, that way f 1. So, then similarly, as for k equal to 0 we are finding. So, already it will be everywhere it will be e to the power 0. So, the next term will be equal to f 2 and this way it will go on and this finally it will be f n minus 1. So, now let us find that is f 1 cap. So, f 1 cap will be equal to, so now start with j equal to 0. So, this is f 0. So, k equal to 1, but j equal to 0 still e to the power 0. So, if e to the power 0, so this becomes 1. So, this becomes f 0. So, plus next term let us see. So, next term it will be j equal to 1. So, this is f 1. So, now it will becomes e to the power I minus I pi into 2. So, for j equal to 1 we are writing. So, j equal to 1, then k equal to 1 here. So, by n. So, this becomes omega. So, f 1 omega. Similarly, you can find this f 2. So, let us, for j equal to 2, this is f 2. So, e to the power, for j equal to 2 let us write e to the power what we are getting. So, we are getting e to the power minus I into 2 pi. So, now j becomes 2. So, j equal to 2. So, this is k equal to we have taken 1. So, this is 1 by n. So, this is 2. So, we can write the square. So, this becomes omega n square. So, then this f 2 into omega n square. So, similarly, we can find f 3 into omega n cube and it will go on. So, this way we can find. So, you just see we can find a matrix. So, this is the matrix we can find. So, this becomes, so we have written. So, f 0 cap you have seen. So, we have written this is equal to f 0 plus f 1 plus f 2, already we have derived this thing. So, this is f n minus 1 and f 1 cap you have seen we have written. So, in the previous slide we have written f n cap equal to, so we have written this is equal to f 0 plus f 1 omega n plus f 2 omega n square and this way it will go on and this becomes f n minus 1 omega n to the power n minus 1. Similarly, if you find f 2, So, this will becomes again F0 plus now it becomes F1 omega n square, then plus F2 omega n fourth. So, this way you can find up f n minus 1 omega n. So, it is 2 times n minus 1. Now, if you write all these things in a matrix form, so then you can have, so you can write this f n minus 1 cap will be equal to similarly F0 plus F1 omega n minus 1 plus F2 omega n 2 into n minus 1 and f n minus 1 omega n into n minus 1 into n minus 1. So, that will be n minus 1 square. So, now you can write down this in matrix form. So, left side F0, F1 cap, F2 cap and finally f n minus 1 cap will be equal to. So, if you take in the right hand side F0, F1, F2 and f n minus 1. So, it will be equal to 1, 1. So, for first one it is coefficient is 1, 1, 1. So, everywhere is 1. For the second line the coefficient starts with 1, then omega n square, then omega n to the power n minus 1, and for the third line it is 1. So, in the first column itself everywhere you will have the 1 and the second column you just see for the third row it will be omega n square, this omega then square of this thing omega n fourth, then omega n square into n minus 1. So, this way you can construct this matrix, so which is known as the DFT matrix. So, you can transform this F0 F1, you can write down the equation in terms of, so if you have n data points, so you can write down this F0 F0 cap, F1 cap, F2 cap and Fn minus cap in terms of this F0, F1, F2 and Fn minus 1 using this matrix. So, it is a n cross n matrix, that is n square. So, the size of the matrix is n square, which is symmetric. The matrix in left hand side is the Fourier coefficient. So, this is known as the Fourier coefficient matrix, the image given. Okay. So, it has a 10 0. So, if you have then depending, so you can write it 2 to the power n form and 2 to the power n form if you have. So, for 10 you can have a 10 is to 10 for example. So, you can have 10 to the power 2 to the power 10. So, you can have this thing. So, to reduce the computational expenses of calculating DFT, FFT uses only n log n order of calculation. So, the matrix what you have seen here. So, for example, let us take a 1024 elements are, let n square equal to 1024. So, in that case, so we can write down this f cap equal to f 10024 f. So, where f 10024 is the DFT matrix with 10024 data points. So, now the above matrix multiplication can be reduced by following algorithm, which is the main objective of this FFT. So, we can, so this matrix can be retained using this odd and even. So, if we are writing this, if we are separating them as the odd number and even number, so this 1024 f can be retained in this form. So, 512 odd will be there and 512 even will be there. So, we have this identity matrix, that is I 512 minus D 512, I 512 minus D 512 into F 5120 and 0 F 512. So, this is F even and F odd. So, this way we can separate this even and odd, and this instead of operating these 1024 a matrix with size 1024. So, we can use two matrix and matrix multiplication with this 512 and 512. Again this 512 further can be reduced, it can be written in this form, this 512 can be written 100. So, here, so starting with 0 to 511, So, the same matrix what you have seen in that, so can be written. So, now the DFT matrix can be, so this is the DFT matrix 512 further reduced to, so it will be divided by 2. So, it will be, so 256, then it can be further divided by 2, and so that way we can go on reducing 1024 to 512 to 256, and finally we can reduce to 2. So, where finally this will be the thing. So, this is 1 and 1 omega n. So, in that form we can write, finally we can write in that form, and we can calculate the FFT of the system. So, using FFT you can have many applications to calculate the derivative and solve the PDEs, then this noise data, analysis of data, compression of audio and images you can use. So, high performance scientific computation you can do using this FFT algorithm, then this digital communication, then signal processing also you can use this FFT. So, to give you some idea, so let us have a 10-second audio. So, you can see that for a 10-second audio, so your n will be equal to, data points will be equal to 4.4 into 10 to the power 5 data points will be there. So, if you are doing DFT, so you have this order of n square. So, it is order of n square, then it becomes order of 10 to the power 11. So, you will have 10 to the power 11, but if you are doing this FFT, so here the order is n log n. So, n log n, so it will be equal to, so you just see, so n log n, so n equal to 4.4 into 10 to the power 5. So, if you do this n log n, so it will be of the order of 10 to the power 6. So, you just see, so you have reduced the size extensively here. So, you have reduced the size from 10 to the power 11 to 10 to the power 6. So, 10 to the power 5 order data reductions you are achieved by using this FFT algorithm instead of using this original DFT algorithm. Okay. So, you can plot the DFT or you can plot the FFT. So, in FFT you can either plot the power, you can plot the amplitude versus time, or you can plot the so you can plot the power spectra versus time. The power spectrum can be obtained by multiplying this amplitude. Actually, this amplitude you can get in, or this FFT you are getting in complex number. So, you can multiply with its complex conjugate to get the power. So, this power you can, so you can plot the power also, power versus this thing. So, let us take some response. So, this is a periodic response. So, you can see a high peak or high, so peak at that frequency, particular frequency. So, you can simulate this thing to see this. For periodic response you are getting a single peak, and with some noise you may get some additional small peaks you may get. So, for a chaotic response you just see you have a band of frequencies. So, it is for a large band of frequencies you are getting this continuous band of frequency. So, in case of discrete system or discrete frequency, so you can have only few peaks and they are not, they are distinct, few peaks will be there, but they are not connected or continuous. But here in case of the chaotic response you can have a continuous spectra and continuous. So, these peaks are there, but this is the dominant peak, dominant frequency, and these are these other frequencies are there. So, these characterize a chaotic response and these characterize a single periodic response in this case. So, let us now see regarding this Poincare section. So, by using this Poincare section, generally we reduce the dimension of the system by 1. So, for example, so if you have, so you have a periodic response, so sine and cosine periodic response is there. So, we have plotted a sine response here, or you can tell a cosine function is plotted here, because at t equal to 0 you have 5. So, this a cosine function is plotted. So, you can plot a sine functions also. So, let this is a response given to you. So, let this is your x t versus time t. So xt versus time t. So you know that, so let us take, so we know, so these to these are these to these is one time period. So this is one time period. So if, so let us have more periods also. So here you can see, so instead of keeping this whole time period, so whole time response, that is xt versus t, so which will consume more space and time, so which will consume more data space to store this thing. So depending on the number of points you are taking in time t, so similar number of points will be there in this xt, and you have to store this xt t versus xt. So it will store a large number of data points. So instead of doing that thing, so if we will sample it at a regular interval of time, for example in this case this is the time period, so let us sample it at a particular interval of time. So you just see, if we sample it at particular interval of time, so you are getting the same point. So here you got this point and same point, so this is the same point we are getting, and if we plot this x versus x dot, x versus x dot. So in case of phase portrait, so you used to plot both displacement and velocity. So in that case you have to store more data also. So you may have to store it using this. So this is t, so this is x and this is x dot. So let you have these 1000 time points you are taken. So in that case, so this will contain 3000 points. So instead of storing these 3000 points, so you just see, so if you plot only this x versus x dot, and everywhere you are getting single point, so you are getting the same point. So for a periodic response you just see, so you got a single point. So this is the Poincare section. So this is the Poincare section of this. So this is the Poincare section of this time response or the phase portrait. So this is the time. So now in this case also let us sample it here. So you just see, so these are the points, same points you will get, and everywhere this is the same point. So you got the same point, and whatever cycles, number of cycles you just take, you are getting the same point, and this is the value. So you are getting, so you can write a code of your own. So this is a code given for plotting this Poincare section. So you can use this code or write your own code to find the Poincare section. So this is a quasi periodic response. So already I told you, if we will write this y equal to 5 cos 2t plus cos 2 root 2t. So in that case, so you have two time. So you have two time period, one time period equal to, this is omega 1 equal to 2 and omega 2 equal to 2 root 2. So t1 equal to 2 pi by omega 1, that is 2 pi by 2 equal to pi, and t2, that is the second time period, equal to 2 pi by 2 root 2. So in this case this is pi by root 2. So this is the smallest time and this is the largest time. So if we take the smallest time, that is pi by root 2, and sample this response, so you can see that we are getting a closed loop. So this is a quasi periodic response. So in case of the quasi periodic response, so this is the Poincare section of the quasi periodic response, and so you just see, this is the phase portrait and this is the Poincare section. So the Poincare section in case of the quasi periodic response is a closed curve. So you have seen now, this is a closed curve in case of the quasi periodic response. So if you have a chaotic response, so in that case you just see, so this is this Poincare section filled of the whole space. So if you sample it with the lowest time period, so you can find the, so it fill up the whole space. So this way, by using this Poincare section, so you can characterize the periodic, quasi periodic and chaotic responses. In case of periodic response, so what I have shown you, so that is the single period. So, instead of a single period, for example, you have y equal to, so take y equal to 2 sin 2t plus sin 4t, so plus sin 8t. So, in this case, so you have 3 period. So, in this case you have 3 period and the response will be, so if you plot the Poincare section, so actually you will get 3 points, actually you will get 3 points in the Poincare section. So, for a 2 periodic, so you will get 2 points, and for a 3 periodic, so here the periods are 2, here the omega, so this is omega 1, this is omega 2 and this is omega 3, and your T1 will be equal to 2 pi by 2, then T2 equal to 2 pi by 4 and T3 equal to 2 pi by 8. So, the lowest time period you can take, so this is equal to pi, so this is equal to pi by 2 and this is equal to pi by 4. So, the lowest time period is T by 3. So, pi by 4, so T3 is pi by 4, this is the lowest time period. So, taking this T3, so if you sample it, so you will get only 3 points on the curve. So, you can plot these 3 points, that is your y versus y dot. If you plot y versus y dot, if you plot, so you have only 3 points. So, you can get the Poincare section with 3 points for that case. So, let us see the another term which is commonly used in case of the nonlinear system, that is the Lyapunov exponent. So, actually Lyapunov exponent or the characteristic exponent associated with a trajectory are a measure of the average rate of expansion or contraction of the trajectory surrounding it. So, you have a, so let us say you have a equation that or flow equation that is written in this form f x semicolon m. So, this is, so m is the parameter which you are changing and this is the state vector x dot. So, if you start with different initial condition, so if it is a fixed point response, so with whatever initial conditions you are starting, so always it will go to that same point. So, it will go to same point, you start with this or you start with some other point. So, this is your x versus t if you plot. So, x versus your parameter, let your parameter whatever parameter you have. So, x versus t let me plot. So, this is time. So, always it will go, in case of the fixed point it is going to this. So, whatever initial condition, if you plot it in phase portrait, so that is x versus x dot, you start with this point, so it will go to this. So, that thing you have seen in the basin of attraction. So, you start with some other point, also it will go to this, it will go to the same point. You start with a third point, so always it will go to the same point. Similarly, in case of periodic response also or the limit cycle, so you have seen, for example, in this case of 100 pole oscillator, so you have seen, so wherever you start, so if you start from the inside point, it is going to this point, you start from here also outside, it will also go to this point. So, always it will go to this point in case of fixed point and periodic or quasi periodic response. So, in case of the chaotic response, but in case of the chaotic response which depends, which varies to a large extent or depends on the initial conditions. So, in that case with different initial conditions, so it will go to different trajectory. So, with slight change in the initial conditions, so there will be a large deviation in the final trajectory. So, to study this deviation in the trajectory, whether they are coming closer or going away, so whether the, so the average rate of expansion or contraction of the trajectory, to study that thing generally we use this Lyapunov exponent. Any system containing at least one positive Lyapunov exponent is defined to be chaotic. So, in case of chaotic response, always this Lyapunov exponent, at least one of the Lyapunov exponent will be positive. The magnitude of the exponent reflects the time scale on which the system dynamics becomes unpredictable. So, the Lyapunov exponent is also a measure of sensitive dependence on the initial condition. Some systems are more sensitive to initial conditions than others. So, Lyapunov exponent is a number that gives us more information and whether there is butterfly effect or not, butterfly effect or this chaotic response or not. So, let us suppose we have two initial conditions x0 and y0. Let the initial distance between them be d0. So, d0 is the initial difference between them, that is x0 minus y0. Change of the distance with time. So, if you plot, let it is dt, that is at time t, let the difference is xt minus yt. So, d is absolute value of the, so it will grow. So, in most of the cases it will grow exponentially. So, we will see how the separation becomes in case of different attractor. So, how we will determine this Lyapunov exponent? So, for a dynamical systems we can write, so this x dot equal to f x m, that is x t equal to, so let us write this slight variation, let us give. So, starting with x0, so if we have a variation yt, so xt can be written as x0 plus yt, then y dot. So, if you substitute it in this equation, then x0 dot equal to 0. So, then y dot becomes f x0 plus, so this is the x dot equal to y dot now. So, x dot as x dot equal to y dot. So, we can write this y dot equal to f x0 y colon m. So, m is a parameter system parameter, or this y dot we can write it equal to, expanding this thing by Taylor series. So, we can write this thing y dot equal to f x0 y m plus d x f. So, this is the first order derivative d x f x0 m y plus higher order terms. So, as this so this f x0 y 0, so that is the initial conditions we have taken. So, this part equal to 0 for steady state. So, so this part equal to 0. So, then our y dot becomes dxf x0 m m0 y. So, this thing, this matrix can be written as A matrix. So, this matrix is the Jacobian matrix what we can develop. So, A equal to del f1 by del x1, del f1 by del x2, del f1 by del xn. So, this way we can construct this A matrix. So, which is the Jacobian matrix. Now, so our equation is y dot equal to dxf into y. So, we can find this by solving this equation. So, we can find, so how with initial deviation of slight initial deviation of y0. So, how much deviation is taking place at time t. So, that way we can find. So, we can write actually this yt in this form also by using this fundamental matrix. So, yt can be written as phi t into y0. So, starting with this y0, so we can here phi t the fundamental matrix of the solution y dot equal to a yt. So, this Lyapunov exponent can be defined at time t tends to limit t tends to infinite 1 by t ln yt by y0. So, this is at time t what is the deviation, by initial time what is the deviation. So, ln of that thing, as the deviation is sometimes very large. So, it is better to take the ln of that thing to get a small number. So, ln of that thing and divide that thing by time. So, limit t tends to infinite. So, that will give the Lyapunov exponent of the system. So, for a multidimensional system, or if the state space is m dimensional, so in that case, so we can write this thing using this I equal to 1 2. So, yi, so it will be yit by yi0. So, that way it can be written. So, one can use this Gram-Schmidt procedure of orthogonalization to find this y1 by 2 ym, and in that case this lambda I can be written as 1 by gamma t k equal to 1 to r ln n I k, where this n is the denominator part, the norm of the denominator part of this y. So, this is n, or this n I is the denominator of the ith term. So, that way one can find by using that equation. So, one can find the Lyapunov exponent. So, here for the Lorentz attractor and Henon attractor. So, the separation, how with initial separation the separation grows has been shown. So, you just see starting with a term 10 to the power minus 10. So, finally, you just see, so there is a separation of 10 to the power 2, that means, so 10 to the power 12 times. So, the separation has increased. So, it increases exponentially. Similarly, here also you can see it is increasing very much. So, if you find the Lyapunov exponent, so you can see some of the Lyapunov exponents are positive. So, that is why, so they are chaotic attractors. So, for commonly used maps and equations, so these are the Lyapunov. So, when you are finding a number of Lyapunov exponents, so they are generally written as Lyapunov spectrum. So, for the Henon map, so the equation, so you can see this equation x n plus 1 equal to 1 minus alpha 1 minus a x n square plus y n plus 1 equal to b x n. So, for the value a equal to 1.4, b equal to 0.3. So, one can find a chaotic response as one of the Lyapunov exponent, you just see lambda 1 equal to 0.603, that is positive. So, that is why one is negative and other one is positive. So, due to the presence of this positive, so then this is a chaotic attractor. Similarly, this Rosler chaos, so x dot equal to minus y plus z, y dot equal to x plus a y, z dot equal to b plus z into x minus c. Taking this value of this a, b, c, so one can find this value of lambda. So, this lambda 1, lambda 2 and lambda 3. So, here you can see this lambda 1 and lambda 2 are positive. Similarly, for Lorentz attractors, we have this x dot, y dot, z dot, x dot equal to sigma into y minus x, y dot equal to x into r minus z, and z dot equal to x y minus b z. So, this is sigma r b are taken this parameter. So, here you can see, so one of the chaotic attractor, so the Lyapunov exponent is 0 and other two, so this is positive and this one is negative. So, here you can find also this is a chaotic attractor. Similarly, this Rosler hyper chaos. So, in this case you just see, so here you have 4 equations and in these 4 equations 2 of them are positive, one is 0 and other one is minus 39. So, here also you can have the chaotic response. So, these are very good references which you may follow regarding this Lyapunov exponent. So, this table actually is taken from this paper Haken. So, H Haken. So, at least one of the Lyapunov exponent vanishes if the trajectory of an attractor does not contain a fixed point. So, you can see at least one of the Lyapunov exponent vanishes, that means one of Lyapunov exponent will be 0. So, if trajectory of an attractor does not contain a fixed point. So, then you can, this is a very good paper where from the experimental time series by this Wolf, Swift and Sweeney and Matsano paper. So, determining Lyapunov exponent from a time series. So, then you can see the paper by the Shimada and Nagashima. So, numerical approach to ergodic problems of dissipative dynamical system. So, then saw strange attractor, chaotic behavior and information flow. So, these are very old papers. So, some recent papers also you can see by Kant, a robust method to estimate the maximum Lyapunov exponent of a time series. This is a very good paper, you may refer. It is published in Physics Later in 1994. Then another paper by Wang, Chang and Kitty Poronchi. So, vibration of initially stressed micro and nano beams. Then you can see the paper. So, a series of paper by Avers, Weiss and Kryasko. So, Aerovip. So, they published, there are many other authors are there. So, they have published this work, this quantifying chaos by various computational method. So, this is simple systems. And then they have also a part 2, vibration of the Euler-Bernoulli beam equations they have taken. So, subjected to periodic and colored noise. So, you can see these papers. So, few more papers are there which are also very useful. For example, this book by this Parker and Chuha, Practical Numerical Algorithms for chaotic system is a very good book, you can follow. Then this paper, this is the earliest paper in this field of Lyapunov exponent. Bentin, Galani and Girogli. So, Lyapunov characteristic exponents for smooth dynamical systems and for Hamiltonian system, a method for computing all of them. So, in part 1 and part 2 both the things you can see. Then another paper here on the computational of Lyapunov exponent for continuous dynamical system. So, this is in 1997 this paper you can see. Estimation of the largest Lyapunov exponent in systems with impact, when the system is subjected to impact, how to find. So, that is given in this paper. Then this is a very good paper also by Muller, calculation of Lyapunov exponent for dynamical systems with discontinuities, where there is discontinuities. For example, so you are taking the friction force. So, for x dot less than 0 and greater than 0. So, there is a jump from minus mu n to plus mu n. So, similar type of systems where there is discontinuity, you may use this type of paper to find the Lyapunov exponent. Then methods, a method for calculating the spectrum of Lyapunov exponent by Jean Twigela. So, you can see this paper. So, for the local map and non-smooth impact vibrating system. So, it is published in Journal of Sound and Vibration. So, when you are studying these chaotic systems, so sometimes they can be written or they can be seen as containing self similar objects. So, they are generally known as fractals. So, several fractal figures have been shown here. So, those who are interested, they can study more regarding these fractals. For example, this is the Mandelbrot fractal, then this is the Julia set, then you can find this fractal picture for many other different type of fractals or fractal sets. So, these are self similar sets which will combine to form the chaotic response. So, you can use all these things to study the response of the system or to characterize the response of the system. So, with this, we conclude this module, and I hope so you will utilize all these analysis or tools for characterizing the time response and study the nonlinear dynamics of different nonlinear systems. Thank you very much.